Hello, are you interested in 3D printing? Look at this beauty. Makes a beautiful sculpture. If you're interested in this, why don't you keep watching, because I am going to do a Mathematica tutorial on how to build things like this and actually print them using Mathematica. Alright, these are great for teaching because, for example, if you're teaching a calculus course in multi-dimensional calculus and vectors, well, then it's useful to be able to use things like this conical 3D print in order to bring to life what you're talking about. Okay? Also, if you just want to learn about 3D printing, you want to learn about how to visualize mathematical objects for yourself, well then stay tuned. Okay, so that's what we're going to do today. Now, I have a template that I use to talk about this sort of thing. Well, not to talk about it, but I'll use it for that now. What I mean to say is that I use this 3D template in Mathematica to remind myself some of the functions and specific codes that I use to build these models. All right, so I would suggest that you do the same. Now I'm opening it up. I'll put it here where you can see it. And let's increase the magnification on that to 300. All right, so look, there are a few ways you can do it, but let's just scroll through and have a look at some of the images first before we talk about how to actually do it. So this one here is the surface that I'm holding here in my hand. It's a well, I guess you call this a quadric surface. Okay, and its equation is z squared is equal to x squared plus y squared minus 9. And we see that here. Okay, let's scroll down and see a few others. That one is not shown. This one, this is a saddle. Another quadric surface suitable for teaching a course in multivariate calculus, right? Because these come up. What I have here are some lines. So I've used cylinders to show lines because they're exactly two lines, I believe, on this saddle that's, depending on the equation, pass through the origin. Okay, so that's what those are. Let's have a look and see what else we have. All right, now this one, it seems that I'll need to make the window a bit bigger. All right, so this is a surface of algebraic geometry. I've forgotten what it's called, but it's a fairly interesting algebraic geometry surface. All right, then this one is the famous so-called Lebesgue, did I say that right? Lebesgue cubic. Again, this is a famous surface in algebraic geometry because it is a non-singular cubic surface, and these kinds of surfaces are said to have exactly 27 lines on them. Now, I'll scroll back up to remind you about what I'm talking about. So this saddle has 2 lines on it, right? Lines that fit entirely on the surface. They're linear lines, okay? The surface is curved, of course, but it has 2 lines on it. This one down here, as cubic surfaces have, non-singular cubic surfaces have, 27 lines on their surface. But this one in particular has all of its lines being real lines and not even projective, I think. Anyway, you can look it up. It's on Wikipedia. But the funny thing is, or sorry, the nice thing is that you can 3D print this. I've got it somewhere 3D printed. Since I moved house, I don't know where I've put it. Okay, so yes, I printed this. Okay, now what else do we have? This is the Stl file. So when you are 3D printing, you want to be able to export your models as Stl files. so that you can then put them to the printer and have them be printed. Okay, so when you show an STL file, you see all of these little polygons on the surface. All right, so up here I have imported the STL file into Mathematica to have a look at it in that way. All right, scroll down. So this one is actually, I think it's actually a cone, I don't know. Okay, that one is clearly a cone. This one, this is, what do you call this? A catastrophe surface. Okay, because in a branch of mathematics, systems of ordinary differential equations, there is something known as bifurcation theory. Okay, so when the parameters, as in the constants in the differential equation, drift over time due to some reason, for example, well, the number of equilibrium points can change, right, suddenly. And this surface depicts that happening. Basically, the parameters drift and it's like moving around on this surface because one axis represents a given parameter, another axis another parameter. And so suddenly you can go from having 3 equilibrium points to having just 1, and that's like falling off of this surface. All right, so that's very helpful when you need to teach such a topic, to be able to hold this and show this to your students and you know, bring it to life, as I said before. Okay, so let's scroll down, see what else. This is the same surface, but you know, plotted in a different range so that it's easier to see what's going on. Okay, and then this one, this looks to me, I believe I got this code off of the internet. Okay, but this is the I forgot what it's called, but it's definitely oh, is this the Lorenz Butterfly? Okay, so this is illustrating a chaotic process. All right, because I believe these are trajectories that seem somewhat random, but they get attracted to some equilibrium points perhaps. Okay, all right, so you can plot that in Mathematica and then give it thickness and 3D print that. I've also 3D printed that. The results were a bit mixed because, well, you see it's quite stringy. So, and here we see that the thickness has been given. All right, so now it's suitable for 3D printing, but again, as I said before, it's a little problematic to do so because it's well, when you 3D print, you've got to build supports, right? Things for the printer, because if the print nozzle comes along like this, and it's got to deposit its print material onto something, right? Not just empty space. So you have to support all of these with some support material, right? So it's not just the model, you have to build supports when you do this. All right, and then let's see, here's just a trefoil knot. All right, like the knots we probably became familiar with as children. All right, so there's an equation for that, looks just like this in parametric form with one letter T. And then you can plot it and give it thickness and print it. Okay, so what do we have down here? Ah, this one. Yeah, look, I think that this was a piece of a wave that I had once used to illustrate calculating a double integral. All right. And then this one, this is one of the favorites here because this is exactly what I said. This is, so here, up here, we've got the surface, right? Here's a surface, and you want to illustrate calculating a double integral. Now, when you first learn about this, you think about it as a sum of rectanguloids, right? Whereas in 2 dimensions, and you calculate the area under a curve, you are calculating the sum of rectangles when you first describe this, right? But when you're doing a double integral, you first describe this in terms of sums of, I guess, rectanguloids. All right, so that's what I'm doing here. I'm illustrating all of these little rectanguloids that you would be adding up. Now you rotate this around, And you can clearly see what we're talking about, right? So as these get smaller and smaller, that calculation becomes more and more accurate. All right, so again, I 3D printed this to show to students. All right, let's see what else we have in this template. What is this one? I don't remember what this is. Okay, Fermat surface perhaps, yes. All right, now this one here. So actually, if I remember properly, this one here, well, I guess you might look at that as a tetrahedral pyramid, right? But one of my colleagues was teaching graph theory, and she had a blind student taking her course. All right, so it obviously would be handy for that blind student to be able to visualize, even though they can't see, but to be able to visualize what this teacher was discussing, right? So that lesson was about group theory and the symmetries of such objects, right? You have these rotations and such, so vertices going to vertices, and you can form a group out of that. But it's nice to be able to show someone who can't necessarily see this, or even the people that can, but have trouble visualizing things geometrically. It's nice to be able to show them a 3D model of this. So I printed that for her so she could help to teach this student and others like it. All right, let's scroll down and see what else we have here. This I think I was attempting to plot the real and imaginary parts of the Riemann zeta function. All right, so this is a very important function in analytic number theory. All right, so I won't talk very much about that. It's just, this came out quite nice actually, because I was able to print this in two colors. So this one surface up here, I printed in, say, black, and the other one in red, and it really brought that to life. All right, let's have a look. This looks like another algebraic geometry surface, okay, called Eniper. And then I believe this one that I'm just getting up to, if my computer goes faster, this is the one that I just picked up before. Okay, and I believe this is an approximation of what's known as a minimal surface. All right, so I'm holding the result up. Now you can see this is just about as big as my head, right? So I printed it quite large. I mean, that took my printer, say 12 hours or so to do it. They're not fast, especially if you want to have a high quality print. All right, but Mathematica allows you to build the STL file suitable for printing it. All right, so this one is just the equation cos of x plus cos of y plus cos of z equals 0. Right, which I understand is an approximation of a well-known minimal surface. Now, minimal surfaces, I believe, have a specific surface area ratio, perhaps with volume. I don't know, but you can look it up. And they're often defined in terms of partial differential equations. Okay, now this is a great one that I was using to illustrate, and I can show you the actual 3D print of this. So I was using this surface to illustrate that sometimes limits of limits, say as xy goes to 0, 0, on a surface, sometimes those limits don't exist because we can approach on one path and get to one point, but we approach on another path and find another point, all right? And so if those don't match, then the limit does not exist. And so this is a great surface for illustrating that. Again, I've plotted that parametrically. Okay, let's have a look. This one. Okay, so this I can see is the same Fermat surface. So let's have a look at the equation. All right, so this is a Fermat surface, x cubed plus y cubed equals z cubed. And I've moved the z cubed to the left-hand side so that I have 0 on the right-hand side. All right, so if you know anything about Fermat's last theorem, Well, it's a famous result that remained unproved for about 400 years until Andrew Wiles proved this result using a special kind of elliptic curve, Frey curve, I believe. Okay, and so this is a special case of such an equation. So Fermat's last theorem says that there are no solutions to the equation x to the power of n plus y to the power of n is equal to z to the power of n in integers when n is greater than 2. All right, so this is an example of n equal to 3, and so I'm able to use contour plot to plot that surface in a given range. And then what I have are lattice points. All right, these balls that you see here would represent integer points x, y, z. All right, so what you would be looking for is points where one of the balls exactly meets the surface. If you want to think about this Fermat surface geometrically, right? But I mean, it's kind of a failure because you see many of these balls that more or less look like they are on the surface, but we know that they're not, right? They just happen to be geometrically really close to the surface, but not on it. All right, so that was an attempt. I'm not sure whether I actually 3D printed this one, but it can be done. It just might be a little bit fragile because these will be vertical rods when you do it. Okay, now what have we got here? So right, this is a way to actually draw something. Now, where's that gone? Where's that gone? So I since found a better way to draw mathematics and 3D print it than this, but this is one of the ways that you can do it. All right, so I think that's all that I have in this template, but that's plenty to be able to do some basic 3D printing using Mathematica. Now let's go back up and talk about some of the really simple ones, okay, so that you can get started doing this yourself. Okay, so now one of the things, now I'm going to move this over and talk about it while I do it. I'll open up a new Mathematica NB file, notebook. Okay, here's a blank one. Window, magnification 300. Okay, I'll put these models down and then we'll start talking about this. So I'm going to copy, first of all, all right. So this what I've copied and pasted right here is a point. All right. So what we're doing is saying, all right, so we've got a point x, y, z, okay, is equal to this. Now, what is that? What is the equation? Well, it's just the equation z is equal to this, right? Or x squared minus 1/2 y squared is equal to z, or z if you're in the United States. All right, but I'm going to parametric plot this, so I want it in this way, and I'm parametrically plotting this over the x and the y. Okay, so let's have a look. So next we write parametric plot. So I'll just copy a piece of the code. Paste. Now look, I can stop right there and just plot that, right? So I'll do that for you. Just Shift Enter. And we wait a little bit and let's see what we have. Okay, so we clearly see a saddle. It's got the mesh on it, right? So that's helpful when you're visualizing it, but you don't necessarily want it when you're 3D printing this. You want to get rid of the mesh, right? So we can say, this is an option now. I'm saying mesh none. Okay, so doing that gets rid of the mesh. All right, plot style, thickness 1. So plot style thickness 1 gives this thickness. It's one of the ways to give thickness to your surface. All right, now you can look at it. You see this edge here has has a thickness. Okay, next, let's look. So you can see some, well, look, I mean, that's a diagonal line there, so you might not want that when you're printing it. You might want to have clean rectanguloid shapes for showing this to people, right? Because you might want to emphasize certain aspects of it. So the next option that is included here is region function z positive. Okay, so let's see whether that makes any difference. Shift enter. Okay, so it seems like I've cut off this surface where z is equal to 0 or negative, and I'm just illustrating the top of that. Okay, now this is called the letter A, which of course you can do in Mathematica. You can give that object a variable, or associate that with a variable. Okay, now next is just a modification of this. So right now I've selected a specific plot range, m equals 16, so that I can go from minus 16 to 16, minus 16 to 16, and be able to change this with one number. Okay, and then we've called that one B. Now next I have the command to export that result. Okay, so I got export, and I've called it saddle4.stl. Okay, so I export this, and then after that I've got %. Right, % means the last thing that was put into memory, basically. But if I want to, at this point, I could put B. All right, so let's just change this. Put B. All right, shift enter. Takes a little while to construct that. And then down below it says basically that it has done the job that you asked it to. All right, now you could go and import that. So let's do that now. I'll just copy this. Copy, import, so you can see the actual STL file. All right, so change this to import. Shift enter, and it will draw this out of my documents folder and show the result as an STL file. Okay, so I own a FlashForge Dreamer. All right, so I don't know if, actually, you know, I'm gonna see if I can get the webcam to point it over there, because it's not far away. All right, so keep in mind I'm moving house. There you go, you can see it. So I've got a bunch of boxes around. Now you see the FlashForge Dreamer. Somebody remarked to me that it looks like a cooking machine. That is there on the dresser. And then you have a look up here on the top of my shelf. I have a giant spool. This is a 5 kilogram spool that I've got on a kind of, I guess you might think of it as a curtain rod. Okay, that's great. Because it keeps it all steady. You don't want things rocking around. And now normally this piece of, what looks like a piece of thread there, that's the spool. Okay, that then feeds down into the machine. So I had to cut it because I moved house a few days ago. Okay, so that feeds in there, and then the machine proceeds to print. All right, so what I do is I put the STL file on an SD card, and I pop the SD card into the side of this. Oh no, that's not exactly right. First of all, I open up the FlashForge Dreamer software. And what I have to do is slice the model. Okay, so I slice the model. That's all fairly easy. I open up the software, slice the model, and make sure it has the appropriate supports suitable for 3D printing. Now, you can, if you don't have a 3D printer, there are a number of services available. So there's a website that just looks around for people willing to offer their services. And that's fairly easy to use. I've used these services, but they tend to be more expensive than doing it yourself. So I thought, well, I'm really going to commit to this and do it myself, even though this printer is not very expensive. Now, another thing I should tell you is that if you're getting into 3D printing, I strongly suggest that you get a 3D printer that does not require a cartridge for the filament, okay? Because when the cartridge, when the filament is inside a cartridge, that cartridge may have a chip indicating how much material is left in the cartridge, right? But what that means is that the company can charge a ridiculous amount for very cheap plastic. Okay, so if you can, shop around and find a 3D printer that 3D prints just from the spool. Okay, now I'm going to go over there and pick up one of the things I'm talking about. So I'll take it back to me, and you can see how my my background works. You see, this is a canvas that I'm moving around here. All right, anyway, I'm going to go pick up this. Okay, here I am with one of these spools. Now, this is probably what they call ABS. So if you're going to 3D print some mathematical objects for showing people, I would suggest doing that with what they call PLA, which is starch-based plastic. I think it's biodegradable, but you can look that up. And what's good about that, other than it may be biodegradable, is that it does bridging fairly well. Now, bridging is when the material allows for the stringy bits to go over what seems like a bridge, because, well, maybe it's a little bit more sticky. All right, so it's good at bridging. So, for example, you see this under here. Now, normally I would have to build some vertical supports in my slicer software to be able to support that. But if you're using a PLA material to do it, then you don't have to use as much, all right? Or you don't have to use as much support material in particular places, right? Because when you have to go and pull this support material off, it can be a bit of a messy process. So you want to avoid it. I don't think you can see it, but here is a place where I had to use supports, and it's fairly rough. All right, so you want to avoid using supports when you can. All right, so back to this. Okay, so parametric plot is one way to do this, but it's not necessarily the best way to build models for 3D printing. Like this, for example, I had to use a plus or minus because this is the surface z squared is equal to x squared plus y squared minus 9, right? And so in order to do that with parametric plot, I would have to do it with both the plus square root and the minus square root, right? Which is not necessarily ideal. All right, so there are other ways to do this. Like you've got command cylinder, for example. Let's have a look. Now, what's going on here? We've given this one thickness, plot style thickness. Okay, but the cylinder seems to already have enough thickness when you give this its radius 1.5 to be suitable for 3D printing. Okay, so let's scroll down and look for something more complicated. Another function. Right, in this one we've got the built-in function contour plot. Now, contour plot is very handy for plotting three-dimensional surfaces in Mathematica. So here you just write the equation of the surface. All right, you don't have to solve for one variable explicitly. You can just use an implicit equation for the surface. All right, but to give these thickness, you use the command extrusion 0.2. Right, and that's what gives it thickness, and then it's suitable for printing. Okay, so so that's contour plot. Now let's see if we can find a variation of giving thickness. I think probably this one. All right, so all right, this one right here. So this is just a command for constructing the trajectories of the Lorenz Butterfly, right, which is right there. And then this, as it is, does not have thickness. But then what we do is we give the option there, plot style tube, and then you can specify the thickness, and that's what gives it the thickness that is then good for 3D printing. Okay, so a number of ways for giving thickness to your three-dimensional objects in Mathematica. Okay, so that's more or less all I have for you for now. So thanks for watching. I hope you learned something, and I hope you can get some benefit out of actually 3D printing things. Okay, bye for now.